So it turns out there are a few other ways for us to use the derivative to help us kind of get a sense for what a graph should look like. So just a couple of things to kind of start us off with, talking about the derivative. So if our derivative is ever greater than 0, so it's positive, on an interval, then the derivative, or the original function, is increasing on that interval. And if the derivative is ever negative on an interval, then the original function is decreasing on an interval. And this intuitively makes a lot of sense for us. So if the initial function is going up, the derivative should be positive. And if the initial function is going down, the derivative should be negative. So if we ever wanted to find the intervals over which a function was increasing or decreasing, what we're going to do is we're going to go ahead and find the places where our critical points are. So first of all, this function has a domain of negative infinity to infinity. And so when we're trying to figure out where it's going up and where it's going down, we're going to look at the derivative. So the derivative of this function will be 20x minus 4. So when we're looking at this derivative and want to figure out where those critical points are, first of all, the derivative exists everywhere. So we can't worry about the does not exist part. Meanwhile, we want to look at where f prime of x equals 0. So if this is what we're looking at for that critical point, then we know that 20x minus 4 equals 0. Then this says that 20x equals 4, and so x will equal 1/5. And this will be our critical point. Now from here, what we're essentially telling ourselves is that we have some sort of derivative, and we want to know what's happening with the function. So, got a couple of points I'm going to end up putting on here. So here's 1/5 on the x-axis. If we're looking at the derivative, what we want to know is, we know it's the derivative equals 0 at this point, but we want to know if the derivative is positive or negative. So what we're going to do is we're going to pick a point, or an x value, on either side of 1/5 to plug in and see what's going on. So 0 is smaller than 1/5. So if we plug in f prime of 0, that's 20 times 0 minus 4, which is negative 4, which is less than 0. So this is something that is negative. So that means that when we're smaller than 1/5 on the x-axis, our function is decreasing. Its values are going down. Now, if we want to head and plug in 1 to the derivative, f prime of 1 is 20 times 1 minus 4, which is 16, which is greater than 0. So over on the right, we have positive values for our derivative. That means the function is increasing on that interval. So it is decreasing on the interval of negative infinity to 1/5, and increasing on the interval of 1/5 to infinity. And when we're saying where it's increasing and decreasing, we're never going to go ahead and include the endpoints. And the reason for that is at those points, either our derivative doesn't exist, so it's not something where we can say if we're going up or going down, and if it's 0, well then it's 0, so it's not technically going up or going down. So this is the interval where it is decreasing, and this is the interval where it is increasing. Now we can use this idea of increasing and decreasing to help us go ahead and find our local mins and maxes. So say we've got some critical point C, then f prime of x If f prime changes from being positive to negative at c, then f of c is a local max. So if it goes up and then goes down, whatever point is there in the middle is going to be a max. However, if we're going from decreasing to increasing, or going from down to up, then that point in the middle is going to be a local minimum, or just a local min. So this is another way for us to go ahead and figure out if we have something that's a minimum or a maximum, instead of having to plug into our function. Maybe we would prefer to plug into our derivative for whatever reason. This is another way to go ahead and find those local mins and maxes. So say we're looking at this example where we've got a function f of x equals x to the 2/3 minus x squared. We want to find the critical points and use the first derivative test to determine whether each corresponds to a local min or a local max or neither. And then we want to figure out the intervals where the function is increasing and decreasing. So we're asked to do a lot here. We want to find our local mins and maxes and our intervals of increasing and decreasing. So first of all, the domain for this function is all real numbers. So this is negative infinity to infinity. So no holds are barred when we're trying to look for those critical points. Now the derivative of this we can find using our power rule. And this will be 2/3, and x to the 1/3 will be in the denominator, minus 2x. So again, to find these critical points, we want to know where f prime equals 0. So this will be 2 over 3x to the 1/3 minus 2x equals 0, which then tells us that 2 over 3x to the 1/3 equals 2x, which will then tell us that we can go ahead and multiply the 3x to the 1/3 over, and so we'll get 2 equals 6x to the 4/3. And then we can go ahead and divide both sides by 6. So we will get 1/3 equals x to the 4/3. Now from here what we'll do is we'll go ahead and raise each side to the 3rd power. And what this will do is this will allow us to get rid of this 3 that's here. This means we'll get 1 over 27 equals x to the 4th. And we can take the 4th root on both sides in order to go ahead and figure out what our critical points should be. Now note that when we take an even root, we need to consider both the positive and negative cases. So this tells us that our critical points are x equals plus or minus 1 over the 4th root of 27, which is roughly equal to plus or minus 0.439. So these two are going to be two of our critical points that we need to look at. We also want to know where the derivative does not exist. And so here, if we're looking at the original derivative, the only thing we have to worry about is, because we have an even root down here, getting a 0 in the denominator. So this does not exist at x equals 0. So this will be, again, another critical point for us to work with. Alright, so what we're doing with our first derivative test then is we're going to go ahead and consider all the different intervals we're looking at. So for the first derivative test, we would like to go ahead and find different places to look at. So we know we're looking at -1 over the 4th root of 27, 0, and 1 over the 4th root of 27 as our critical points. Again, this was approximately -0.439, and this was approximately positive 0.439. And so we need to make sure that we're picking values on our intervals that we can go ahead and try to plug in for the derivative to check out our function. So if we wanted to pick a value between that was smaller than -0.439, one option would be -1. And so if we plug in -1 into our derivative, that'll help us know if we're increasing or decreasing. So our derivative, again, is 2 over 3x to the 1/3 minus 2x. So we'll have 2 divided by 3 times -1. Be very careful with parentheses, to the power of 1/3 minus 2 times -1. And here we'll get roughly 1.3 repeating, which is 4/3. Don't want the inverse, want the fraction version. So that is 4/3, which is positive. That's the important thing here, is that over here we have something that is positive. So our function values are increasing before we get to -1 over the 4th root of 27. Next, we want to pick something between -0.439 and 0. So what we might do is we might pick something like -0.1, because that'll be on this interval. So what we can do is we can go ahead and use the second entry function on our calculator until we get back what we had initially had, and then we can go ahead and make some insertions here and there in order to put in those decimals we need. So now we've got -0.1 as opposed to -1. We can change what these x values are. So we'll have this plugged into our derivative, and we can see that we end up getting a negative value on this interval. So that means we are decreasing over the interval. Next, we want to look at being between 0 and positive 0.439. So now what we can do is consider something like a positive 0.1. So going ahead and deleting the negatives here and here, we get a positive 1.236. The important thing is that it's positive, and so over this interval, we'll be going up. Now we know that we're getting to not exist here, and we're 0 here, so everything between this, we never hit 0. Because we never hit 0 in the middle there, we're never going to change from being positive or negative. So we know we'll have positive values everywhere else on this interval as well. And then last, we want to pick something greater than this. Easiest thing to do would probably be to just pick 1. So if we go ahead and make it so that we have 1 as the thing we're plugging in, we end up with a -4/3, or a negative value. So we go from increasing to decreasing to increasing to decreasing. So what that means for us is that all these intervals where we're positive, we're increasing, and all these intervals where we're negative, we're decreasing. So we are increasing on the interval -∞ to -1 over the 4th root of 27, unioned with 0 to 1 over the 4th root of 27. So this is where our derivative is positive, and we are decreasing on those other intervals. So where we're looking at negative 1 over the 4th root of 27 to 0, and 1 over the 4th root of 27 to infinity. Rewrite that. 1 over the 4th root of 27. So this is just where we're increasing or decreasing, but this does not tell us where our local mins and maxes are coming from. So remember, if we go from going up to going down, we have a local max. And if we are going down to up, we have a local min. And so when we're looking at the places where we go up to down, that'll be at both of these x values. So this is just talking about where the local maxes and mins are occurring, not what they are. We still need to plug into the function to know what the values are. So we've got a local max at x equals negative 1 over the 4th root of 27, and x equals 1 over the 4th root of 27. And a local min at x equals 0. Alright, so that's an example then of how we would go ahead and use the first derivative test to determine where our local mins and maxes would be occurring. Now there's some other terminology and other things we can use to help us determine the location of a local max. We say that a function is concave up on some interval a to b if the derivative is increasing. So concave up is going to look something like this, where even though our values are going up, they're going up at or going down at an increasing rate. On the other hand, the idea of concave down means that our derivative is decreasing on some value a to, or some interval a to b. This would be something like this or this. So notice that we're saying this is where the derivative is increasing. So remember that when we said that our function was increasing, its derivative was positive, and when our function was decreasing, the derivative was negative. But we also saw, or we're now seeing, that the derivative has to be increasing or decreasing. And the derivative is a function. So that means that when the derivative is increasing, the second derivative has to be positive. And when our first derivative is decreasing, our second derivative has to be negative. So this is the same as saying f is concave up if f double prime is positive. And this is the same as saying that f is concave down if f double prime is negative. So we've had critical points before. A point C, f of C, will be called an inflection point if the concavity changes at x equals c. So either it'll go from being concave up to concave down when x equals c, or vice versa. And so notice we're calling this a point. So this will be both the x value and the y value of the original function as we're looking at it. Now we can also use the second derivative to help determine where we have local mins and maxes. This is an alternative to using that first derivative test instead. So we're going to let c be a critical point of a function. If the second derivative of c exists, the second derivative of the function at x equals c exists, then if the second derivative is greater than 0, then f of c is a local min. So again, if we have something that is concave up, the idea is that it is going to keep going up. And so we've got some c right here where we went from being negative to positive, but our derivative was going and becoming increasing during that time. We have a minimum value at that point. However, if the second derivative is less than 0, it's negative, then f of c is a local max. So again, we're saying we have some critical point here, and we have a concave down function. So that meant we were going from increasing to decreasing. And so our derivative was decreasing during that time, which means the second derivative is negative, and that means that we went from being positive to being negative, and so that critical point will be at a local max. However, if the second derivative is equal to 0, then what that tells us is that we should use some other test, like the first derivative test. So say we had some sort of function g of x where we wanted to go ahead and use the second derivative test to determine where the local mins and maxes occurred. So here what we'll do is we're going to go ahead and start off by getting our critical points. So our original function exists everywhere. The domain is negative infinity to infinity, which will help us with our critical points. The derivative of this will be 4/3, or 4x to the third, minus 16x. Now, that is g prime, not f prime. G prime exists everywhere. Now, while we're taking the first derivative, if we're going to use the second derivative test, we might as well find the second derivative as well. G double prime of x will be the derivative of this function, which will be 12x squared minus 16. So here we need to figure out where the derivative equals 0. So we want to know where 4x cubed minus 16x equals 0. We can go ahead and factor this to get 4x times x squared minus 4 equals 0. And from here we can go ahead and solve for our different zeros. So this would be 4x equals 0, x plus 2 equals 0, and x minus 2 equals 0. If we go ahead and break this up into being 4x times x plus 2 times x minus 2 equals 0. So this tells us then that our critical points are x equals 0, negative 2, and 2. So now that we have our critical points, we're going to plug the critical points into the second derivative. So we get g double prime of 0, which is going to be equal to 12 times 0 squared minus 16, which will be negative 16. And this tells us that we have a local max. G double prime of negative 2 will end up giving us 12 times negative 2 squared minus 16, which is a positive 32. And G double prime of 2 will give us 12 times 2 squared minus 16, which will also be 32. So we have a local max at x equals 0, because that's where the second derivative is negative. And we have local mins at x equals negative 2 and x equals 2, because that's where our second derivative ends up being positive. So second derivative here, very helpful for us to quickly determine whether or not we had a local min or a local max at a particular point. Now we also can go ahead and determine intervals over which our function is concave up and concave down. So remember, if the second derivative is greater than 0, we say that the original function is concave up, and if the second derivative is less than 0, that's when we say that our function is concave down. So note that the second derivative test does not give us information about whether or not a function is concave up or concave down over a whole interval. It's really just telling us about a particular point. So for this function here, 1/4 x to the 4th minus 2x squared, we're going to go ahead and find the inflection points and determine the intervals of concavity. So remember, the inflection points are where our second derivative is equal to 0. And that will be where we switch our concavity. So say we wanted to look at the function, this is what it looks like here. Inflection points are just the critical points of the second derivative. So this is where f double prime equals 0 or f double prime does not exist. And this is, the intervals of concavity are just looking at where we're up or down. So our first derivative of this function is x to the 3rd minus 4x, but we're really interested in the second derivative of this function, which is 3x squared minus 4. And so again, we want to know where it doesn't exist or is equal to 0. This is something where the second derivative will exist everywhere. So when we want f double prime to equal 0, we're taking 3x squared minus 4, setting it equal to 0, which means that 3x squared equals 4, which means that x squared equals 4 over 3, and so x will be equal to plus or minus 2 over the square root of 3 as our points of inflection, which are roughly equal to plus or minus 1.15, in case we're trying to figure out good values to go ahead and plug in above or below those. So these tell us where we think our inflection points will be, but we only are going to have inflection points if the sign changes. So possible x values for inflection points. But the concavity has to change first. So what we'll do is we'll do what we've been doing and make some intervals for ourselves. So we've got -2 over the square root of 3, 2 over the square root of 3, and we want to go ahead and find things that we can plug into our second derivative to know whether or not we are concave up or concave down. So some points we might pick between them is 0. If we're looking for something that is smaller than this, this will be -2. If we're looking for something bigger than this will be 2. So again, we'll just plug into our second derivative to find what we're looking for, positive or negative. So 3 times -2 squared minus 4, after we fix the typo, will be 8, which is something that is positive. If we go ahead and plug in 0, this will instead give us -4, which is negative. And if we go ahead and plug in 2, we'll get something that is 8, which is, again, positive. So we're looking at these, trying to figure out where we are concave up and concave down, and where we're switching. So when we're positive, we're concave up, and when we're negative, we're concave down. So at both of these x values, we switch our concavity. So if we want to go ahead and find the inflection points, then what we'll be doing is we'll be plugging back into the original function. So if we had f of -2 over the square root of 3, this will be us taking our -2 over the square root of 3 and plugging it into this function. So it'll be 1 over 4 times -2 divided by the square root of 3, all raised to the 4th power, minus 2 times -2 divided by the square root of 3, all raised to the 2nd power. And so this, math frac, gives us -20 over 9. And if we go ahead and plug in our positive 2/3, now we will go ahead and do the same thing, except instead of plugging in -2/3, we will plug in a positive 2/3. And now we will get, again, -20 over 9. So if we're asked about our inflection points are -2 over the square root of 3, -20 over 9, and 2 over the square root of 3, -20 over 9. If we're asked about our intervals of concavity, well, we are concave up, on the interval -infinity to -2 over the square root of 3, and from 2 over the square root of 3 to infinity. And we are concave down on the interval -2 over the square root of 3, 2 over the square root of 3. Alright, so just some things we want to make sure that we're kind of keeping in the back of our heads. We want to know what our signs of our derivative, first derivative and second derivative are telling us about our original function. So here is f, here is f prime, and here is f double prime. If our derivative, our first derivative is increasing for our function, then our function is going up. If our first derivative is negative, then the function is decreasing. If the second derivative is going up, then we are concave up, and our original function or derivative is increasing. I did not give myself near enough room. And if our second derivative is negative, then our first derivative is decreasing, and we are concave down. All right, so the remainder of the exercises that are in this note packet are just some questions to go ahead and give you guys a little bit more practice with these ideas of concave up, concave down, and finding these mins and maxes. What I'll be doing is I'll be posting the completed note packet on Blackboard, and you guys will have opportunities to kind of ask questions about what's going on in the discussion board and give these a try before kind of looking at those.